This is a revision video for P5h Lenses and lens diagrams. Lenses are found in cameras, telescopes, glasses, and in the eyes of most animals. There are lots of different types of lens, but they all work in the same way. A lens is used to refract the light that passes through it. The lens forms an image. The two types of lenses you need to know about are convex, which are these ones, and concave, which are these ones. This lens is called biconvex as both sides of the lens are convex. This lens is called a plano-convex as only one side is convex while the other side is flat. These lenses are called concave lenses. This one is a biconcave as both sides of the lens are concave, and this one is plano-concave as one side is concaved and one side is flat. A convex lens is an example of a converging lens, which means that as the light rays pass into the lens, they are refracted so that they will eventually converge and cross the principal axis. This will give a focal point. When drawing ray diagrams, we always put this line through the centre of the lens. This is called the principal axis. We also normally draw this line through the centre of the lens, which is called the optical centre. Now we said before that the convex lens will eventually make the light rays converge, so if I carry that on and make them cross, there will be a point on the principal axis where those two lines meet. This is called the focus of the lens. And the distance between the optical centre here and the focus here is called the focal length of the lens. Now these things need to be drawn on every ray diagram that you do. Every ray diagram will have a principal axis, every ray diagram will have an optical centre, will also have a focal point or a focus and a focal length. The power of a lens is measured in diopters. It can be calculated using this equation. The optical power equals 1 divided by the focal length of the lens, which must be in metres. We'll work through the example here. A convex lens has a focal length of 5 centimetres. What is its optical power? So for this one, we want to calculate optical power. We've been given focal length, and we know that we need to do 1 divided by the focal length. So the optical power equals 1 divided by focal length. Now we shouldn't put 5 centimetres there because it needs to be in metres. But 5 centimetres is 0.05 metres. So the optical power of this convex lens will be 1 divided by 0.05, which gives us 20 diopters. You can stop the video now and have a go at these two questions below. Question 2 will require you to rearrange this equation to work out the focal length. If you struggle with this, try putting the equation into a triangle first and it'll help you to rearrange it. We're now going to talk about how to construct ray diagrams. In reality, light is reflected from all parts of an object, but this would make our diagram very, very complicated. So what we do is we consider the light that is being reflected from the tip of the object. And we always draw our object as an arrow. The arrow shows the direction in which the object is pointing. So in this case, the object is upright. Light is being reflected from the tip in many directions, but we can find out where the image will be by considering light that follows one of the 3 paths. The first path is light passing through the optical centre of the lens, which is this one, the blue one. This ray is not refracted and passes straight through in a straight line. The second path is light that is travelling parallel to the principal axis, which is the red line. Now when that hits the optical centre, it is refracted by the lens and passes down through the focus. Then the third path of light is this one, light that travels through the focus first here. Then when it hits the optical centre, it's refracted and comes out parallel. So this lens has got two focal points. This is a convex lens, a converging lens. Rays of light that come in parallel to the principal axis will hit the optical centre, they will be refracted, and they will come out, cross the principal axis. At the point at which they all cross this axis is the focus. And then remembering from our diagram earlier, the distance from the focus to the optical centre is the focal length of the lens. If we consider the rays of light that are following a different path, so they're coming out from the focus and they are diverging from the focus or spreading out, when they hit the optical centre, they will be refracted and they will come out parallel to the principal axis. In general, a fat lens has a very short focal length because it refracts light more, and a thin lens has a longer focal length because it doesn't refract the light as much. Now where the rays of light cross, the focal point or the focus, this is where an image is formed. Digital cameras, for example, produce tiny images on film or on light-sensitive chips. Digital projectors produce large images on a big screen. These kinds of images are real. They can be focused onto a screen or a film. Real images can be formed on a screen or surface using a convex lens. Whereabouts would you place a screen in order to form a real image with this lens? Start by thinking about where the rays of light cross, and it's here. So where would we place the screen in order to see this image? Well, we'll place our screen there, because the image is formed where the rays of light cross their paths. The characteristics of the image produced depends on whereabouts the object is in relation to the principal focus. Now the principal focus is here and here, the point at which the light rays cross the principal axis. So in this diagram, our object is quite far away from the lens. It is more than 2 times the principal focus away. Now the image forms where the rays of light cross. Now if we look at our ray diagram, we can see that the image is closer to the lens than the object was. It is smaller than the object, and it is inverted, or it is changed and now is upside down. It's also a real image because we can put a screen there and we can focus it. What you can do now is stop the video and try and draw the ray diagram to show how an image is produced when the object is less than 2 times the principal focus away from the lens. Okay, so if you had a go at that, you should have found that your diagram looks something like this. If the object is closer to the lens, then the image will have different characteristics. Characteristics that this image has is that it's further away from the lens than the original object. It's larger, it's inverted, so it's upside down, and it's also real because we can place a screen there to focus our image. Now in both of those cases we've just talked about, the image formed is different size to the object. This means that the lens has magnified the object. In this one, it's made the image smaller, and in this one it's made the image bigger. You can calculate the magnification of a lens using this equation. The magnification equals the image height divided by the original object's height. Magnification has no units, as here we've got a height divided by a height, so the units will cancel out. If you get a magnification of 1, then it means the image is the same height as the object. If you get a magnification of greater than 1, then it means that the image is larger than the object. If you get a magnification less than 1, then it means the image is smaller than the object. Now see if you can use that equation from earlier, the magnification equation. If you can't remember it, then skip back and write it down. You need to use it to be able to work out the magnification in these questions. If you stop the video now, you can have a go at these. We're now going to talk about how a magnifying glass works. A magnifying glass uses a single converging lens. The object needs to be close to the lens for it to work. The object also needs to be nearer to the lens than the principal focus. Here is a ray diagram for a magnifying glass. Notice that the principal focus is here and our object is in between the principal focus and the lens. The characteristics of the image is that it is larger, it's upright, and it is further away from the lens than the object is. It's also a virtual image. It's a virtual image because the rays of light only appear to have come from the image. They don't actually come from the image itself, so there will be nowhere you can put a screen to form an image. If you look at our object, the rays of light come from the top of the object there. But when you look through the magnifying glass, your eye carries on the lines until they meet at this point, and that is where your eye will see the image formed. However, these are not actually rays of light, so you can never place a screen there to form an image. Okay, now that brings an end to this revision video on P5h, lenses and lens diagrams.